Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. In this lecture, we are going to discuss another asymmetric catalysis named reaction, that is Sharpless Asymmetric Dihydroxylation reaction. Previously, I have discussed about Sharpless Asymmetric Epoxidation. That is actually a different reaction. Okay, so I suggest you please read that lecture also, because both are important and they both have distinct differences. For example, Sharpless Asymmetric Dihydroxylation uses osmium as a catalyst, whereas epoxidation reaction uses titanium 4 plus as a catalyst. Here ligand is a cinchona based ligand in case of dihydroxylation. In case of epoxidation, that is a tartarate ester. Tartarate ester is the ligand here. So there are lots of difference, but both reaction has a very unique advantage. Both are responsible for the oxidation of alkene into the corresponding either epoxide or diol. Okay, so a lot of interesting topic will be learned in this lecture, so I request you please watch until the end. Okay, so the most important point of this Sharpless Asymmetric Dihydroxylation is it resulted in higher enantiomeric excess. And what is the advantage? Because we know that asymmetric catalysis, we need to have a particular enantiomer in higher enantiomeric excess, generally greater than 90%. Okay, so lots of things, and in this case, in this reaction, osmium is a catalyst, there is a asymmetric ligand, potassium ferrous, this thing is a oxidant, and amine as a accelerator for reaction. So a lot of interesting chemistry will learn. So let's go into the details. So today's lecture will cover mainly few points, like first of all, the recapitulation of osmium tetroxide mediated means non-asymmetric dihydroxylation. After that, how the asymmetry could be introduced, then mechanism, then ligand, metal binding and the active site structure, and finally some examples with conclusion. Okay, so let's start. So here you can see that osmium tetroxide first reacts with the alkene, and this thing is actually a addition reaction. In some cases it is addressed as 3+2 cycloaddition, in some cases it is addressed as 2+2 cycloaddition followed by insertion or rearrangement, and which ultimately results in this molecule which is named as osmate ester. Okay, so just look at very carefully. In the first case, we have taken osmium tetroxide, which is actually +8 oxidation state, and which is reduced ultimately in +6 oxidation state. Okay, and in this case, what happened, that osmium is reduced, alkene is oxidized, and ultimately produce this ester, and this ester undergo hydrolysis to produce that osmium 6 species and the diol reagent. Okay, by the way, see, I have written here that 2 hydroxyl group is in opposite, but don't get confused. This is a strategy to make you confused, and such kind of confusion may create in the exam hall. Actually, they are cis-diol, but how this can happen? By a CC rotation, because the bond is actually, so this is CC rotation, and the bond is whatever here actually a sp3 carbon-carbon bond. Okay, so that's why rotation possible. Now, so we have understood that this reaction possible, but the biggest disadvantage of this process is this reaction is stoichiometric. Okay, so if it is stoichiometric, what is the problem? You need one equivalent of osmium 4+2 oxidized this alcohol into the corresponding diol. But where is the problem? The problem is actually, first of all, the osmium tetroxide is costly. Okay, second, it's volatile, and volatile means its boiling point near about xylene or toluene, you may think like that, around 130 degrees centigrade. Fine, volatile. And another thing, osmium is not that much widely available, so costly, volatile, and another point is that toxic. So for that reason, it is highly desirable, can we develop a method in which that reaction could be catalytic? Is it possible to use catalytic? Actually possible. Means what will happen, that this osmium 8 species will be further oxidized, osmium 6 species will further converted into osmium 8 thing during the reaction, and for that thing we need another oxidant. In this case oxidant could be NMO, means N-methylmorpholine oxide, or morpholine N-oxide, or tertiary butyl peroxide. This tertiary butyl peroxide part I have discussed previously about Sharpless asymmetric epoxidation. I shall provide the link, please visit there. I will not explain here, but let's discuss about the N-oxide part. N-oxides are nothing but, see, this is actually, this is N-methyl, N-oxide, this is, and oxygen. So what happens, this oxygen part is transferred for the oxidation purpose, and ultimately what is the fate of this reagent? Fate of this reagent is N-methylmorpholine, the neutral molecule. Okay, so in this case we know the addition of oxygen means oxidation. Okay, oxygen is highly responsible for this. And by the way, I have already uploaded lectures about pyridine N-oxide, where you can clearly understand such kind of chemistry in details. I shall provide the link, you may visit if you want to learn further details. Okay, fine. So now another important another interesting topic here is that amines. See, these amines, tertiary amine, are capable to accelerate the reaction. And how this process happened? By coordination with the metal center, that is osmium. And this is a very important point for to construct its asymmetric version. Why? Because when amine coordinates to the metal center and increases the reaction rate, so if we use a chiral tertiary amine, better to say tertiary amine, chiral tertiary amine, that could be our ligand to get the asymmetric counterpart, means enantiomeric excess. So let's discuss that way, how the asymmetry could be introduced into the reaction. Okay, so the point is origin of chirality or enantiomeric excess for this reaction. Just one important statement, please remember always, chiral environment produces chiral product. So when we want to get chiral product, we need to provide chiral environment. Chiral environment means a catalyst covered with a chiral molecule, you may consider, means catalyst metal center covered with a chiral molecule. Okay, so this is chiral. So what will happen? Chiral means it has different substituents, and different substituents in 3D orientation results a different arrangement. So consequently a particular way the ligand could interact to the metal center. Okay, so that will dictate, it will result a particular product, means better to say particular stereoisomer. Okay, and that is responsible for the enantiomeric excess, or EE. Now we have understood that to get a chiral product we need to use a chiral product. Now a simple question may come, who will produce the chiral product for us in bulk amount with good enantiomeric excess, such that we can take that molecule, that better to say in this case tertiary amine, and do that. And best example is nature. Okay, mother nature, not only nature, we should respect nature as mother nature. Why? Because mother nature is so selective for a particular isomer. For example, naturally we use D-glucose or L-amino acid. Okay, so mother nature is so selective that it chooses this, not the other isomer. So in this way we can say that if we try to explore mother nature properly, we can find out our desired tertiary amine which is needed, and we can use that tertiary amine as a catalyst which will coordinate to the metal center and provide the enantioselectivity. Let's discuss that thing. And for this purpose, what we choose? For this purpose we choose ligands, that is cinchona alkaloid. Okay, and from cinchona alkaloid we found out two types of ligand. One is dihydroquinone, which is in short abbreviated as DHQ, and another is dihydroquinidine, means this one, which is abbreviated as DHQD. Okay, these two if you use in the reaction mixture separately, it will result a different enantiomer. Okay, and other condition, keep it in mind, will be everything will be same. So chirality, for chirality these two are responsible responsible for EE. Okay, now sometimes people get confused, are they enantiomer? No, they are not enantiomer. Just look at everything. Maybe this is see the ethyl group, they are not in the image position, mirror image position, so they are not enantiomer. Okay, fine. Now this is actually the main ligand you may consider, but scientists have found out some better version of this ligand which produces better conversion, and for that reason they have found out this DHQ FAL. DHQ means DHQ twice FAL means DHQ dihydroquinone, and FAL means phalazine. Okay, actually this part of ring is known as FAL. This is the phalazine ring which connects to this kind of asymmetric unit in a same molecule. So this is the overall tertiary amine ligand you may consider, which is used for the process in widely amount. Now one is DHQ twice FAL and another is DHQD twice FAL. Okay, just remember, I shall explain how will be the mnemonic device to remember. You don't need to memorize the catalyst structure, just remember. Okay, by the way, in market this ligand mixed with some other thing sold as reagent, and that is named as admix alpha and admix beta. Actually they are nothing but mixture of potassium salt, that is potassium 8, potassium 8 which is equivalent to I made mistake. This osmium salt which is equivalent to osmium tetroxide, and potassium ferrocyanide, and this potassium ferrocyanide is the oxidant for regeneration of that osmium 8 species. I'll explain everything after some time. Fine. And along with that K2Cr3 which is made responsible the pH maintain, that is basic, and this DHQ FAL is actually responsible for asymmetry. Okay, so osmium center is the catalytic center. Now another part is actually admix alpha is this one, and admix beta everything is same except the ligand. Here this DHQD FAL. So we know the asymmetry is introduced because of the ligand, and in this case we are changing ligand. So what we can think, that whatever enantiomer will produce from this, for example A, in this case the another mirror image of that enantiomer will be produced. Okay, so this will result two different products, but they are different from stereochemistry point of view. Okay, so now let's try to understand the mnemonic device. Okay, means how to determine previously what will be the product. For this purpose, in this case two type of ligand could be used. One is DHQ ligand and another is DHQD ligand, which I discussed. Just how to remember this, see this DHQ part is a 3-word, and in this case it is a 4-word. Okay, we know 4 is greater than 3, and means 4 is in higher, so you may consider 4 is in higher position than 3. So if it is in higher, we can say it is on the top. So if you see this 4-letter ligand, think that hydroxylation will be on the top side, so this is top. And if it is a 3-letter, 3 means down, so this must be in down phase. Okay, so in this way the reaction will occur. Another thing, this reaction is nothing but a electrophilic epoxidation. Actually osmium tetroxide mediated epoxidations are electrophilic epoxidation, means that this double bond is actually the electrophile. Okay, means it should be electron rich, means if it is electron rich, reaction will be better. Osmium C is in +8 oxidation state, so you can consider that the metal center is electron deficient, so that is a nucleophile. Fine, so this, and in this case if you take electron rich alkene, that will show higher reactivity compared to electron deficient alkene. Fine. By the way, in contrary to this statement, there is another type of epoxidation, that is nucleophilic epoxidation, in which we take this alpha beta unsaturated carbonyl compound, and here ultimate product, that is this epoxide, is produced by the two reagent, that is hydrogen peroxide and sodium hydroxide, and how the reaction happened, this mixture produces this HOO minus, which act as a nucleophile as well as the epoxidizing agent. That's why this is called nucleophilic oxidation. I have uploaded a distinct lecture. I shall provide the link. Please visit for clear understanding. But I suggest you please understand these two strategies, electrophilic epoxidation and nucleophilic epoxidation. If you understand these two, I believe it will be easier for you to remember the complete chemistry. Okay, fine. Now let's discuss the reaction mechanism with asymmetric ligand, asymmetric 3-degree amine ligand. Okay, so what happens? First we use osmium 8 reagent. So first osmium 8 reagent reacts with the ligand, means ligand coordinates. In this case, better to say tertiary nitrogen ligand coordinates here. So this is the, you may consider this part, this catalyst is right now chiral catalyst. Okay, why? The chiral ligand is attached to this, which will allow the reactant to attack to the metal center in particular 3-dimensional orientation. Okay, then after that, if you react with this alkene, what it will do? It will result in the osmate ester. Okay, fine. And after that, what it will do, as I explained this mechanism, after that there will be a hydrolysis here. So it will produce the cis-diol, better to say a particular enantiomer or enantiopure or higher enantiomeric excess. Fine. Now what is the fate of this osmium? It is reduced. Now how this could be regenerated? This osmium could regenerated by potassium ferricyanide. And actually no, cis, this iron, just don't be confused about ferricyanide or ferrocyanide. I know it's confusing. Just it is iron 3 or iron 4. Think about it. Okay, how do you can see what is the charge? FeCN6 3 minus. Okay, means iron's oxidation state is +3. +3 is the highest oxidation state generally for iron, and in this case what iron can do? Iron can convert into iron 2. So if it is 2, then the final charge will be 4 minus. So K4 FeCN6. Fine. So for that, during that process, how many electron it is taking? It is actually taking 1 electron. Okay. But for osmium 6 to osmium 8 oxidation, how many electron need to be withdrawn? 2 electron withdrawn. So for that purpose, we need to use 2 molecule or 2 equivalent of this potassium reagent for that target purpose. Okay, so in this way this is acting as the oxidant. Fine. Now what is the clearly happening in case of chiral tertiary amine? Previously, just remember what we told, that is a tertiary amine. I never told pyridine derivative. So this nitrogen or this nitrogen, don't be confused. Only one tertiary amine was there. This is this one, or I have written previously in this one. Okay, so it will coordinate, and just you can visualize, try to visualize that. See, osmium center is crowded, surrounded by this big ligand, so this big ligand will provide this molecule a chiral environment, okay, which is responsible for chiral product. By the way, actually for transalkene selectivity is more, but for less for cis-alkene. That is the reason I have showed here the mechanism with transalkene. You may confuse that, sir, what about cis-alkene? So this is the reason why cis-alkene generally not preferred for reaction with this, because enantioselectivity is poor for cis compared to trans. But for this is, since our asymmetric reaction, we always expect that it will result higher enantiomeric excess, and for that purpose transalkene is better rather than cis-alkene. Okay, so generally example you will find mainly about transalkenes. Fine. So let's discuss few examples. Now the easiest example, it is a trans derivative of this alkene. So see what we have taken. This this osmium salt. Okay, and actually in this case osmium is in 6 oxidation state, +6 oxidation state, which will be converted to 8 by this K3 FeCN6. Okay, fine, we have discussed. So in this case, just look at the ligand. What is given? In this case, given DHQD fal, 4 letter more, so epoxidation will be above position. And see the enantiomeric excess 97%. Interesting. And other reagent, this sulfonamide act as an additive which increases the reaction rate. Tertiary butanol act as a solvent. This tertiary butanol water mixture act as a solvent, and temperature of the reaction is 0 degree, which means the reaction occur under milder condition. Okay, fine. So this is the thing. And another interesting point, just look at 1 mole % catalyst, it's pretty less. Okay, so this catalyst and this 0.2 mole % ligand is capable for the process. Okay, so that is the very interesting point on selectivity of this reagent. Now it was a previously very simple alkene. Now if you will consider a little bit about different substituted alkene, obviously it is expected that this double bond is relatively lesser electron rich compared to this one, but still this reaction can occur. Okay, as I told, this is the electrophilic epoxidation, so activity may be less but selectivity may not be less. Okay, so that's why, see, in this case we have used DHQ fal, means 3 letter. 3 letter means low, means epoxidation will be, oxidation will be in bottom side. So here the bottom side oxidation happens, means hydroxylation. So you get, and see the enantiomeric excess is 96%, it's pretty high. Okay, let's discuss some other example. So in this case, you can clearly see that 2 types of double bond is there. This is actually a terminal, and another, this is actually internal. Okay, so now question, where the epoxidation will occur? As I told previously, it's an electrophilic oxidation. So electrophilic oxidation will occur on that part which is electron rich, and we know internal alkene are better electron rich, better to have due to having more substitution on this alkene part. Okay, so if substitution, more electron rich reaction will happen here. And see, here admix beta is given, by the way. Another thing, during the question you may find such kind of information, what is beta and alpha. Okay, so as from our English alphabet, first A comes, then B comes. Similarly, alpha is first, then beta. So just remember in this way that alpha is first, means lower, beta is higher. So alpha means it's before, means lower, like 3. So alpha is 3, beta is higher, means 4. So alpha means DHQ. So this alpha means actually DHQ and beta means DHQD. Just it's a mnemonic strategy, how can you remember it? Okay, so it is alpha. The example was given in case of beta. So 4 letter higher, so the the oxidation will occur, means hydroxylation will occur in the above position. And look at the yield is 71%. That's okay, acceptable. But see the enantiomeric excess, this is 94%, and this is the beauty of this process. Now look at the example number 4. Here 2 double bonds are given, and question where will happen and why. First of all, this is given DHQD 4 letter, so above, hydroxylation will above side, fine. From top side hydroxylation. Question, which double bond, either this one or this one. See, this is double bond 1 and this is double bond 2. Double bond 1 is closer to this electron withdrawing group, that is ester. Consequently, double bond 1 is electron deficient. Okay, so if it is electron deficient, so epoxidation is difficult here compared to that in case of 2, which is relatively electron rich. I suggest write the word relatively, because if you write electron rich, this word is meaningless. Compared to whom is more electron rich? So that's why relatively and then the 1. Okay, so consequently the reaction occurs at this side, and the final example, see, this is a terminal and this is the internal. Just we have learned previously that internal is more electron rich, so epoxidation will occur, fine. So and 4 letter given, so it will be top side, fine. But in this case, this hydroxyl group I haven't mentioned stereochemistry. Question why? See, this is attached to 2 methyl, here 1 methyl 1. So this center is not asymmetric. Okay, so if it is not asymmetric, whether I write it's above or bottom, it is meaningless. So that's why you may find such kind of example where the asymmetric, this position here, one case position is mentioned, other case not. Okay, so what we have learned from this, let's make a summary, and this example will help you to understand that is details. So that is a cis-hydroxylation of chiral alkene. Okay, why chiral? See, we have taken a particular enantiomer of this below. So we will check what is the advantage or what thing we are getting in extra compared to this admix alpha and beta, means in absence or presence of chiral ligand, what difference we are getting. We will learn this part. Just look at this. If you use the non-asymmetric condition, so this is actually a non-asymmetric condition. See, only osmium tetroxide is given and NMO means it's an oxidant, THF water, no ligand is given, asymmetric ligand. So what we are getting, actually we are getting yield means 83% yield, and where the A means this two product, A 76%, B 24%. What is the conclusion of this statement? That not acceptable from asymmetric catalysis point of view. Why? Because for asymmetric catalysis, generally what is expected, the EE should be greater than 90%. That is the criteria. So it is not. So it is not acceptable. Whereas if you take admix beta means higher, 4, it will be top. So beta means higher, so it should be higher, it should be 4, so it should be top. Just remember in this way. So we can accept that the dihydroxylation from the top side will be major product. An interesting point, see, the overall reaction yield 83, 82, 85 means almost close, but the asymmetric selectivity changes, so you will learn. So we expected that dihydroxylation will occur from the top side, fine. So in this case selectivity is 98% and the bottom side 2 means you may consider that's a very less, so greater than 90%. Whereas if you take for same reaction admix alpha means low, means the epoxidation should be bottom side. So what is the yield is similar, but in this case the bottom part having 95% selectivity rather than the 5% of top dihydroxylation product. So what message we are getting? We are getting the ligand actually capable to change the product completely with a enantiomeric excess higher than 90%, and that is the beauty of this process. So we can consider this is a stereo-selective dihydroxylation. So this is the conclusion of this discussion. This is a stereo-selective dihydroxylation reaction, whereas changing the ligand you can clearly observe the selectivity change from 98%, and here the opposite product can produce 95%. Isn't it interesting? Okay, so this is the end of this discussion. What you have learned? We have learned the asymmetric electrophilic dihydroxylation, fine, as I told, and stereochemistry of the product could be predetermined, and in this case admix alpha results in dihydroxylation on the bottom part, lower number, beta results in top part. You may confuse that, sir, why you are saying the same word repeatedly, such that if you listen more time it will be easier for you to remember more time. That's why I am saying repeatedly. Okay, the third point is the trans alkene show better selectivity than the cis, and electron alkyl is more reactive than electron deficient because it is electrophilic epoxidation. Okay, electrophilic epoxid, sorry, not, I'm sorry, I began dihydroxylation. If I make any mistake during the talk, please excuse me, because two are similar, so I make the mistake. Product. The product is a cis-diol. It's a very important. Why? Because for asymmetric catalysis we need chiral, pure chiral product, and if we can get higher enantiomeric excess, then we can use this for the next reaction, another for during the asymmetric synthesis. Okay, so this is the overall discussion for today. If you really like my teaching, I request you press the like button and show your like. Yes, say that you really like the lecture, and write your opinion about my teaching in the comment box. If you think this video is really worthy, then share with your friends, and if you think this channel is very helpful for you and worthy, then subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon such that you will get the notification of every single video I upload. Okay, so thank you for watching. Stay happy, stay blessed. See you in my next video.